Right, this is chapter 5.2 lecture. Remember, 5.1 temperature, thermal energy, and heat. Thermal energy or temperature is nothing more than the measurement of the kinetic energy of the particles that make up that object. Thermal energy is the total potential and chemical energy of those particles. And remember the kinetic theory of matter. All matter is made up of tiny particles. Those tiny particles are in constant motion. At higher temperatures, the particles move faster. At lower temperatures, the particles move slower. And at the same temperature, more massive particles move slower than less massive particles. And we want to get the kinetic energy of those particles. That's temperature. Thermal energy is the total again. Thermal energy is the total of potential and kinetic energy of those particles. All right. Remember, heat. Heat always flows from hot to cold. Heat is energy that is transferred between two objects due to temperature differences. It always moves from hot to cold. Warmer objects always heat cooler objects. All right. And then specific heat, that's how we raise the heat of an object, and we do that, measure that with a calorimeter. All right. Conduction, convection, and radiation. Conduction is the transfer of thermal energy by the collision between the particles that make up matter. So by these particles colliding, and let's take a look at a Newton's cradle. This might help a little bit. Watch the energy, the kinetic energy, the thermal energy. If these were tiny little particles.
Oh my, Newton's cradle, a large version of it. This was popularised, I think, by Loncraine and Broxton in the late 60s, the swinging 60s, that's nice. And it's never been out of production since then. Many different sizes.
So you can see those collision of particles. That is a transfer of energy through the collision of those particles. Usually happens in solids. When you're cooking, it's showing here how if you have hot soup or a hot pan of water, a metal spoon will transfer that energy up the spoon and cause it to transfer to your hand, and it'll burn your hand. So conduction is transferred by the particles bumping into each other. All right, those little particles in the matter. What makes a good conductor? Anything where the particles are close together and it's easy for it to transfer energy, transfer that thermal energy wherever the particles, and usually metals. This is density. Measurement of how close these particles are together is density. Right? The closer the particles are, the more dense the material. So this would have a high density, and this would have a lower density. Okay. The density of water, by the way, is 1. Convection. Convection is a transfer of thermal energy in fluid. Now, what happens in convection and convection currents? All right. I'm going to draw a little beaker here. I'm going to put some particles down in here. And we'll draw a little flame here, heating it up. As this heats up, as an object heats up, it expands. Okay. And as it expands, that means the particles that are originally like this are now like this. This warmer liquid, the warmer liquid where the particles are spread out farther, is going to rise to the surface. It's less dense. The most dense material will stay down here. That's why when you throw a rock in water, it sinks, because the particles are closer together in the rock than they are in the water. A piece of wood floats on water because the particles are farther apart in that wood than they are in water. So the piece of wood will float. So as these particles spread out, it causes them to go to the top. They come up here, the air hits them. We have air coming in here. They cool off, and as they cool off, they're going to drop back to the bottom. They heat up, they're going to move to the top. They cool off, they move to the bottom. And this is what a convection current is. As it heats up, it rises. As it cools off, it goes back down to the bottom. I don't know how great my picture is there, but that is a convection current. That is a convection current. You can see it in a lava lamp, all right? You can see that convection current in a lava lamp. All right. Sorry about cutting off there. I had to get a drink. But all right, deserts and rainforests. I'm going to talk about our convection current where we live. If you can just imagine for a minute, it's called the Alberta Clipper. Sometimes the convection current moves a little bit south. And when it moves a little south and it gets towards the Belleville area, the air, since it's a little farther south than, say, Canada, Alberta, where it comes from, it's warming up and it rises. The air warms up there and it rises around Belleville. If it comes from the south, if the Alberta Clipper moves a little bit north, and what happens is the convection current south of the Alberta Clipper now is cooling off and dropping. The air drops. So around Belleville, sometimes the air rises and sometimes it drops. It's right in the area of two different convection currents. And if it drops, that is, if the bad weather comes from the south, if bad weather, the snow, is coming from the south, most likely we will not have school or a 2-hour delay. If it comes from the north, I think I've been at Clear Fork now for 14 years, maybe 3 or 4 times it's come from the north and we haven't had school. But if they tell you we may have a lot of snow, and you watch the weather and it's showing the weather north, like around Cleveland and that being really bad, chances are we're going to have a 2-hour delay. If it's coming from the south, on the other hand, 2-hour delay or no school, trust me. I know all you have to do is watch that pattern. So that's what it's explaining right here, is about convection currents in the air and how it affects our planet. If you notice here in Africa, we have deserts here and a nice lush green jungle in the middle. That's due to the convection currents. Okay, that's due to convection currents. All right, radiation. If you remember, going way back to the 4 basic forces: force of gravity, the electromagnetic force, and then the strong and weak nuclear forces. The electromagnetic force is radiation. Okay, energy from the sun gets to us through radiation, but it's through electromagnetic waves, and you can see that right here. Okay, electromagnetic waves. That's what gives. That's how radiation travels to the Earth, is electromagnetic waves, and that makes it's a long range force, just as gravity is. So that's how the sun's rays reach the Earth, and it warms us up. So we can have transfer of thermal energy through conduction, which is particles touching. We can have it through convection, and then we can have it through radiation. All right. Then we have good thermal insulators and good thermal conductors. And you can see it crosses into biology here, and it tells you how a seal's blubber and these penguins' blubbers keep it warm, and how these scales help to heat the body of the lizard. All right. So what makes a good thermal insulator? Anything where the particles are farther apart. A good thermal conductor is where the particles are close together. Okay. And it talks about insulation in buildings. That pink insulation that you put in there, there's a lot of empty space in it. So that's good stuff. Thermos bottles work the same way. The way a thermos bottle kind of works, I'd rather talk about, and I know the reason I'm going to tell you about windows is because it was on the air test years ago. So here's my window. Doing the best I can there. Sorry. And of course, the window's made up. It's got particles jammed in there that glass does. Okay. And this is, we'll make this the cold area outdoors, and this is indoors, the hot area, warmer area. All right. What happens is the heat, remember, heat travels from hot to cold. It's going to hit this window and it's going to transfer out really easy. Boom, into the cold. So what they do is they make double pane, triple pane windows. And what a double pane window is, and that's what most houses have these days. Here's my two windows. My double pane window means there's two pieces of glass. All right. And we know that this is full of particles that are jammed tight together. Okay. But what they do in this area in the middle is they vacuum out all the gas. So there's barely any particles in here. When the heat comes and hits it, there's nothing in the middle that's vacuumed out. So the heat's going to stay inside and the cold will stay outside. All right. Because there is a gap in here with no particles. Triple pane glass is even better. Now, you know, if you have a double pane glass and it's lost its seal and this is filled up with gas, you get water on the outside of the windows. Okay. You'll get damp. What's it called? Oh, well, you'll get the water on the outside, condensation. You'll get condensation from the seal being broken. So, all right, that is it for this lecture. I hope this helps you with your homework. Make sure you watch the notes and read, read, read.